Hello and welcome to Cracking the Cryptic. It's Mark here, just setting up Simon's Solve. Now, you've seen, if you've followed the channel, that Simon occasionally plays little tricks on me. This time, I have this killer Sudoku that's come from ahaupt, and I've tested it, and I've sent him a message that it's a nice little solve, perhaps despite appearances. We will see how he gets on with it, because I am here to tell you this is one of the most monstrous things I have ever solved. Good luck to him. We'll see how he gets on. I'm looking forward to it. See you later.
Hello, welcome to Wednesday's edition of Cracking the Cryptic, and on screen we have another puzzle by ahaupt, who's fast becoming one of my favourite constructors actually. He's, I think we've done 2 or 3 of his puzzles on the channel. They've always been exceptionally interesting. He is an absolute master of sort of Sudoku geometry, and so I hope this will be a good puzzle for today. It appeared on Logic Masters Germany yesterday, and in the preamble ahaupt says it needs some arithmetical tricks to solve it. Now, killer Sudoku is one of my absolute favourite types of Sudoku. This is just a partial killer Sudoku. You can see the cages don't cover the whole of the grid. But yeah, this I'm very much looking forward to. The comments, I think it's had 4 people have solved it so far, and the comments have been along the lines of, this is the best killer Sudoku I've ever seen in my life. I got Mark to test it. I sent it to him last night. Mark said it's actually quite approachable, this puzzle, so I'm hoping it won't be too hard. So if you are new to killer Sudoku or variant Sudoku, you should definitely have a try of this one. It should be quite doable. Now, with that, anything else I want to mention? I do want to say a huge thank you to those of you who've tried our Sudoku puzzle hunt, which came out on Saturday. We are still getting lots and lots of correct entries sent in. I would say probably 10 every hour. And all of the comments have been amazing, so we've been so thrilled. We think we did get the difficulty level right, because it does seem that everyone who's put a serious attempt into it has solved it in the end, but it has been a struggle that you seem to have enjoyed. So yeah, we're delighted about that, and if you haven't tried it yet, then you can find it on our Patreon page, which has a link under the video. Now with that, let me a quick reminder of the rules of killer Sudoku. What we've got is you can see little numbers in the top left hand side of all the killer cages. Well, these tell you the sum of the digits in the cage, so these yellow squares would have to sum to 26, and the only other rule is that you can't repeat a digit in a cage. So that's obviously very obvious for this cage down the 9th column. Obviously if we had a 7 in here, we couldn't then have another 7 in the column, but it's slightly more tricky to see in some of the bendy cages. But it's not possible to say for that digit and that digit to be the same number, because they are part of the same cage. And that's all there is to it. So do have a go at this. As I say, Mark says it's quite doable, and you can play the puzzle by clicking the link under the video. And with that, I'm going to have a go. Let's get cracking. So, normal place to start with killer Sudoku is to find the restricted cages. So 17 is a bit restricted. You can only make 17 with 1, 2, 3, 4 and 7, or 1, 2, 3, 5 and 6. So you always know there's a 1, 2 and a 3 in a 17 cage. Apart from that, there's actually very little in this. You can see we've got lots of sort of Tetris shapes, but all of the digit totals for these Tetris shapes are not very helpful. So I don't think this is the place to look. Let's look at the top right hand side, where we've got well, 28 cage is a little bit restricted. It's a bit like the 17 cage. You can only make it in 2 different ways. It's got to have an 8 and a 9 in it, and then it's either got a 5 and a 6 or a 4 and a 7 to give you the extra 11 that you need. But actually all of these Tetris shapes, its symmetrical grid, are also not very useful, or at least not useful to me. So sometimes what you have to do with killer Sudoku is you've got to use the geometry of the grid. So if we have a look at what I mean by that, well, we can use the rule of 45. So these yellow squares in box 3 here, we know those squares will contain all of the digits from 1 to 9, therefore we know those squares add up to 45. Now, sometimes you can find overlaps with the cages that have given totals that allow you to do some nice geometry. So here the geometry is anything but lovely, though. It looks tricky to me. So the only way of doing that on this cage is going to be to say we could sum all of those cages, and if we did that we'd get 81. So we now know that in order to reduce that 81 to the number 45 we need, we have to go 81 minus those 5 squares plus that square equals 45. Well, is that useful? It's not greatly useful, I don't think. I mean, I guess we could... The difference between 81 and 45 is quite a lot. It's 36. So we know these 5 squares have to add up to at least 37 then, because this will have to have a positive value. That is a bit restricted actually, isn't it? So because these squares all have to be different, they could be a maximum of 6, 7, 8 and 9. Therefore this square definitely needs to be at least equal to 7. So that is a 7, 8 or a 9. So 30. So the absolute maximum I can make these 5 squares is 39. In which case this would be a 3. So this needs to be 3 or less. So there we go. I've managed to get 2 cells restricted to 3 possibilities each. How is this easy? This is not an easy puzzle at all. I think I'm missing something very obvious here, because this definitely doesn't feel easy. I tell you what, maybe I try the same trick down here. Look, this time we've got 51. So this is more minimal, isn't it? So 51. So in order to reduce 51 to 45, I have to deduct out all of those squares and add in this square. So the minimum I could make those 5 squares is 11. I make these 1, 2, 3 and 4 and this one a 1. That's 11. So that gets me down to 40. So this square always has to be 5 or greater. Well, that's even less restricted than that one. What on earth is going on here? I'm so sorry if you guys have spotted the trick here, but I definitely haven't. This is very odd. Maybe I can add up. Maybe if I add up all of the squares. Hang on, let's do that. So if I add up all these yellow squares, I get 35, 65, 105. That means nothing to me. Absolutely nothing. Let's try that up here. Maybe we get a more useful looking total. So if we add up all of these, we get 44, 51, 71, 79, 99, 125. So this is 125. This is 105. And that's... I'm running out of ideas here. The only other idea I've got is that somehow I've got to relate these two areas of the grid to each other somehow. So I know that the total of a whole Sudoku grid is 405 because it's 9 lots of 45. So if I've got 105 here and 125 here, that's 230. So the rest of the grid has to sum up to 175. But we've got 2 45s, lots of, so 90 there. So what I've managed to do is to prove the white squares add up to 85. Is that what I've managed to do here? And that's useful somehow. What is going on? This is not easy at all. What is... Tell you, I'm going to ring Mark Goodliffe up after this video and ask him what he's talking about. This is not an easy puzzle. So there's some mad geometry we can try, and I've got nothing else, so I'm going to try it. There's a relationship. Yeah, let's have a look at this. So if we highlight these 4 squares here, or not 4 squares, 16 squares, but these are common to the last 4 rows of the grid and the last 4 columns of the grid. So they do allow us to build a relationship between the 2 totals that the only 2 totals we've got in the grid for these areas. It's a bit tenuous, but let's have a look and think about it. So we know that those 4 rows of the grid will sum to 4 lots of 45. That's 180. So how can I write 180 using what I know about the grid? I can say 180 is equal to the red square plus all of these squares. Well, that's another 105. So the red square plus 105 plus this square, that needs to be in there, minus those squares. So 180 is equal to the red square plus 105 plus purple minus blue. Now, the reason I said we can relate the shapes together is that we've got the same restriction down here. So again, we've got 180 being these 4 columns is equal to the red square, this time plus 125. We need to add that square in. Let's make that square grey, and we need to deduct out those 3 squares. So we've got, and the idea, of course, is that once because we know both of these totals that we've just built equals 180, we can just set them equal to each other. So what we've got now, and we can cancel the red square because the red squares are common to both sides. So what we get is that the purple square minus the blue squares, purple minus blue, 105, is equal to 20 plus grey minus green. So how on earth is that helpful? So purple minus blue equals 20 plus grey minus green. Actually, I've just noticed that, look, we can do the same up there. That's the same. I was looking down here, but we've got the same restriction. Look, we've got the same sort of square 4x4 bit of the grid. So if we did the same trick on the top left of the grid, we would establish a relationship between these squares. So it's the same relationship. Oh, there's something going on here, isn't there? This is... I just wish I was clever enough to understand what it is. Purple minus blue is equal to 20 plus grey minus green. I'm so sure that loads of you are shouting at your screens here at me. Purple minus blue equals 20 plus... Ah, no, hang on. I can use... Purple plus green. Oh my good grief, this is not easy at all. This is absolutely gorgeous, but this is not easy at all. So we're on the right lines here, but what we have to realise is that these are all in the same column and these are all in the same row. And that tells you why this 20 number is so important. Oh, good grief. So what we've got to do, and it's going to be hard for me to do this, so you might have to I might put a card on the screen, but let's think about these equations. We've got purple minus blue equals 20 plus grey minus green. Now, if I bring over to one side of that equation the whole of this column, then I'd have purple plus green is equal to 20 plus grey plus blue. Now, why does that matter? Well, it's because these are all in the same columns now. So they have to be different numbers. How can I make two quadruples different by a value of 20? If all the numbers in the quadruples, all the numbers in this quadruple have to be different, all of the numbers in this quadruple have to be different. Well, it's very, very hard indeed. The only way of doing it is if I make these as massive as I possibly can. So let's make them 6, 7, 8 and 9. That's 30. If I make these as small as I can, 1, 2, 3 and 4, I get 10. The difference between 30 and 10 is, what do you know? It's 20. That is what we're meant to be understanding. Oh my goodness, I've never ever seen that in a killer Sudoku before. That is absurdly complicated, but absolutely beautiful. I love that that sort of thing is happening as well. I'm pretty sure ahaupt came to Sudoku setting from watching Cracking the Cryptic, and he's just taken something that is, it's a puzzle that's 25 years old, and created something, you know, a trick I have never seen before. It's absolutely unbelievable. So now we can start the puzzle. We know that this is a 6, 7, 8, 9 quadruple. We know this is a 1, 2, 3, 4 quadruple. And we know that is a naked single, the hardest naked single in the world ever in the history of Sudoku is that 5. That is a 5 because it can't be a 1, 2, 3, 4 or a 6, 7, 8 and 9. And I'm not going to say we're cooking with gas. We are not cooking with gas. We are cooking with something very old and unignitable. That's what we're cooking with, but at least we are cooking now. Oh, and look, this is why this... Yeah, so if we'd done it the other way round, you can see we'd have compared these squares, and you can see from the Sudoku now, these ones have got to be 6, 7, 8 and 9. These ones have got to be 1, 2, 3 and 4, and that's what we would have established if we'd started up here. Holy moly. Mark, what is Mark talking about? This is one of the most brutal tricks you can possibly imagine in your life. And this was very approachable. I think they were his exact words. Bobbins. I think you know what I'm really thinking. I will say bobbins. Now, can we do some Sudoku then to get further with this? Yes, we can. This 24 cage is now force, look. The maximum I can make those two squares is 17, so I need to make these two 3 and 4 to make that work. So this, we are off and running. Those two can't be 3 and 4 now. The 30 cage is now restricted, look. What's the maximum I can make those 3 cells? What's 7, 8 and 9? That would be 24. So I still need 6 more. Well, I can only get to 6 more if I take the absolute maximums from those two squares. That gives us a 1 here. That's not 1 therefore, or 4. Those aren't 4. There's a 1 in one of these two squares. These squares are 7, 8 and 9. Ah, that gives us another digit here. Look, we've got 7, 8, 9 triple. This has got to be a 6. And another 7, 8, 9 triple. Ah, but we can do a little bit of a trick here. Look, this 7, 8, 9 triple, we know that the 7 is in one of those two squares, i.e. in this box the 7 is in one of those two positions, so that can't be a 7. 1, 2, 3. This square is a little bit restricted. Look, it's 6, 7, 8, 9 in the column. It can't be 1 or 5, so that's got to be 2, 3 or 4. Same is true of this square, which sees 7, 8 and 9 in its row. It sees 1, 5, 6 in its box. That's 2, 3 or 4. So this square has to be 7, 8 and 9 to complete box 5 of the grid. The 6 is ruling out 6 from those cells. Oh, now look, there's a nice restriction there on this box, this 24 box. Because if we look along this box, if I make this a 7, 8 or a 9, then these 3 squares would be a 7, 8, 9 triple. That adds up to 24. That's not going to work because there's still 2 more cells to fill in this box. In fact, these 2 cells can be a minimum of 3 if they were 1 and 2, which means these squares can be a maximum of 21, so we can't have a 9 in any of those squares. So these have to be 6, 7 and 8. That's got to be a 6. So there's no 6 here. These are 1 and 2. The 1 here fixes that this is a 1, this is a 2. This can't be a 2 now. 7, 8 here means that there's a 9 in one of those 2 squares. Look, that's really nice because that means this can't be a 9. That's an 8, that's a 9. This is an 8. That can't be an 8, so there's a 7, 9 pair here, so this becomes an 8. That forces that one to be a 7. It's in the same box. Oh, it's beautiful, as always, from this guy. It just is a very, very beautiful setting. That can't be a 2, look, because the 2's here. 8 must live in one of those 2 squares in column 5, so it can't be there. Where now? Oh, 1's here and here. That's a 1. Ah, now that's interesting, isn't it? Now all of a sudden we can maybe do our 45 trick on this box after all this time. Because we've got, what have we got? We've got, let's highlight this, we've got these squares add up to 51. So in order to reduce this 51 to just the 45 in this box, we need to 51 minus the 1, that's 50, plus the 9 is 59. So these 4 squares have got to add up to 14 to bring us back down to 45 again. So these have to add up to 14. Well, that's really important because we know there's a 1 in one of these 2 squares. So if we try 1 and 3, these 2 squares would have to add up to 10. But they can't be 7, they can't be 1, 9, they can't be 2, 8, they can't be 3, 7, and there's a 4 there, so they can't be 4, 6. So these can't be 1 and 3, these have to be 1 and 2. Therefore, this is a 3, therefore that's a 4, this is a 2. 4 means this is a 4. Now this 20 cage can't have a 9 in it anymore or it'll go bust. So there's no 9 in that cage anymore. This has got to be a 1. The 7, 8 here fixes this as a 9. This is a 7, this is a 9. These still have to add up, what was it? 14 I wanted. I've got 3. So these have to add up to 11 without using 2, 9, 3, 8, 4, 7. These have got to be 5 and 6. 5 and 6. Now the 17 is interesting because that now can't have a 7 in it because it contains a 5 or a 6. So this is now a 1, 2, 3, 5, 6 version of the 17 cage. That forces a 4 into one of these cells, forces a 4 up here. That can't be a 4. 8 now must be in one of those two squares in box 7 from these 8s operating. That locks an 8 up there as well. These squares, they've got to be 3, 7 and 9. No, we can't quite resolve that yet. That's not 3. 3, 7, 9. These two have got to be 5 and 6 to complete the row. Oh, now look, the 28 cage, we know it's got 8, 9 in it. It needs 2 more cells to get to 11. And now, as this square's got to be a 5 or a 6, it's got to be a 5, 6 pair, not a 4, 7 pair. And the 6 here means that must be a 6. It's got to have a 6 in it, this cage. So that's a 6. That's a 5. These squares have got to be 5, 8 and 9, therefore. 5, 8, 9. 27. Those squares have got to be 1, 3 and 4. That can't be 1. 27. Oh, here's something, look. That domino is interesting to me because this domino sees the whole of this Tetris shape in the 28 cage, look. So that domino can't contain a 5, 6, 8 or a 9. So the maximum digits we can put in there are 4 and 7. Oh, but 4 and 7 breaks this cage because 4 and 7 add to 11. These two squares would have to add up to 16. They'd have to repeat the 7 because they'd have to be 7 and 9. So this is not 4 and 7. But it must have a 7 in it, mustn't it? Because if it doesn't have a 7, it would be 3 and 4, and that means those squares couldn't be big enough. So there is definitely a 7 in here. That means that square's got to be a 9, because it can't be a 7. This is not a 4 in either of those squares. So this has got to be, this must be an 8 then. That's the only way this works. This has got to be 3, 7. This is an 8. There's no 8 here now. This 8 sees that square, 8 and 7. The 7 bounces back, gives us 7 and 3. That's not 3, therefore. The 5, 9 now fixes that this square's got to be an 8, because obviously the 5, 9 is, the 9 is already in the cage. That's a 9. Those squares have got to be 2, 4 and 6 to complete the box. That's not a 4. Well, it's definitely going better now, but I would venture to say it's still not easy. 8s here and here mean that's an 8. Look, that places the 4 as well. We need to put a 7 in column 1. This 7 means it's not that square, so that's a 7. That's a 9. This 9 here fixes the 9 and the 3. It's got to be a 3 in one of those two squares. In fact, we're running out of steam here, aren't we? We've used up an awful lot of the cages. So the only 4's here and here. That forces that one to be a 4 by Sudoku. So I was going to say what we've got to do now is either Sudoku or we've got to use the cages we've had. Well, there's only 2 cages we've not used. We've not used the 16 cage or the 18 cage. So maybe where the 8 goes, is that what we meant? Yeah, that looks nice, doesn't it? So if this 8 was here, these 3 squares would have to add up to 8. These 2 squares would have to add up to 7. They'd have to be 2 and 5 because the 3, 4 is ruled out of that square. So this would be a 2, 5 pair. That looks possible, actually. Maybe we can rule the 8 out from this square. So if this is an 8, these 3 squares have to add up to 10. So that can't be a 6 because we can't put a 3 here. So if this is an 8, this has to be a 5. Let's just look at that. 8, 5. These 2 squares have to add up to 5. They can't. The 3, 4 is not possible in this square. And with the 1, 2 there, this would have to be a 3 or a 4. So actually, we are able to say this is not an 8. This is the 8. So this is an 8 by Sudoku. These have to be 2 and 5 now, don't they? So this can't be 4. This is a 4. This is 2 and 5. And I think we're slowly but surely managing to eke out 1, 3, 6 here means this is a 5. This is a 2, 1, 6. We're starting to get there very slowly. This is a 7 by Sudoku. That's a 7 by Sudoku. Look at these 7s operating on the grid. That forces that to be a 7. That gives us a 3 here. So this can't be a 3 anymore. That's got to be a 2 or a 5, which creates a 2, 5 pair there, look. So that should be a 6, that should be a 2. 2, 5, 3. That square's got to be, what's that going to be? A 2, I think. That 2 fixes the 2 and the 5 at the bottom. That fixes the 5 here. We're looking for a 1 and a 6. Wow, what a puzzle. That can't be a 1. Now, hopefully, it's going to be plain sailing now. We need 5, 6, and 7 into those squares. This can't be 7. This can't be 5. Maybe this column, look. What do we need here? 1, 3, and 7. So that's got to be a 3 or a 7. That's got to be 1, 3, or 7. Oh, yes, look. Look at that. I mean, even that step, it's not that easy. There's a triple in the bottom row on 3, 6, and 7. So this little one can't be a 3 anymore. That's going to be a 4. That's a 3. So let's keep focusing on the bottom row. We still need to put 2 and 9 into the bottom row. The 2 here fixes the order. That's 2. That's 9. That gets us the 9 and the 5. Does it just peter out there? Maybe it does. So we still need 3, 4, and 6. So that's got to be 3 or 6. This has got to be 4 or 6. This one has got to be 1, 4, and 1, 5 here. 1, 4, 5 here. What am I missing here? Sorry. Actually, what am I missing here? What a... It's still being difficult. Right, I've got something. I mean, it's a bit convoluted. I'm sure I'm missing something very, very obvious here, but look, we've got a bent triple there. 3, 6, and 7 bending round the corner, but the important thing is that one of these cells sees the other 2. So this one hiding in the corner here definitely sees that one, definitely sees that one. Why is this important? Well, it allows us to do some logic. If this is a 3, this square's got to be a 6. If, on the other hand, this is a 7, that square's got to be a 6. So we know for certain there is a 6 in one of these yellow squares in the finished solution. Now, if that's true, this little square here can't possibly have a 6 in it because it sees both of those alternatives. So this is a 5, that's a 1, that's a 4, 3, 1. Now hopefully that's going to... that does look like it has broken it, doesn't it? Broken it in a good way, as in the way that says I actually might be able to finish the puzzle. That can't be a 1. 6 here gives us a 7. That's a 6. This is a 3. That's a 5. And hopefully... Yes! Right, where is Mark Goodliffe's phone number? I am so sorry if you try this puzzle, unless I've missed something at the start and there is a really easy way to start that puzzle. That is absolutely horrendously hard. It's gorgeous, don't get me wrong, but it's not a basic puzzle. It is not a basic puzzle. I hope you enjoyed me or watching me struggle through that and getting ever more perplexed as to what was going on. And yeah, as I say, I'm about to go and phone Mark Goodliffe. See you later. I'm cracking the cryptic.